play with the parameters, what we did, I only give you one example here. But the major aspect you should remember is the history list lets these probabilities run on the same line, and only if you have reached the maximum number, then the adversary somehow can learn something. So if you, to keep these two lines more together, you have to extend the history list, but at some point in time, of course, it's finite. There will be a drifting apart of these two lines. So this is more or less the kind of algorithms we looked at, first of all, to maintain perfect privacy, and then what I called probabilistic privacy, giving up a little bit and therefore getting more efficient algorithms. So that's the trade-off. Any questions so far? Go ahead. I know that you are much more...
Interesting. I have a question. So the history represents a kind of crucial information here.
Right.
So you needed to keep it a kind of...
we recognized only, if
secret,
we looked only at the probability and only relied on the pool, then this gap was much wider.
No, I know, but I say, since you rely on the history, right? So what if the attacker can get hold of the history list?
Always assume that the history is in your secure coprocessor.
But again, so would that be reasonable? Because if you have multiple users,
well, if you start to write it out as well, even encrypted, then the adversary might learn something through the access pattern on this history. And then we haven't looked at that. But you see, then that's actually where we stopped, because we felt, first of all, the student ran out of time. And second of all, it made us aware that maybe the next step to really advance this would be to be more systematically look at the ways that you put in these kind of fudge factors, which are, what kind of properties should these fudge factors have in order to be most effective or to allow the adversary to deduce the least information possible. And we haven't gone to that point.
Yeah, but I have also,
research.
I don't know.
No, you are the only one. Go ahead.
No. I don't know. I don't want to take all the time for questions.
No.
So anyway.
We have, I only look at the
No,
watch.
I have a more general question. So suppose that this encrypted database is outsourced to another publisher.
Yes.
Then how can this publisher have access to the unencrypted database as well?
In one of my algorithms, I said I keep two copies. Yeah.
I know, but
if you have the other one, if you only want to protect the access to the database, he could also have the unencrypted one. That means he knows the original values, as long as you don't want to hide your medical record. Fine.
But my question would be exactly, what if you want to protect the confidentiality of the data and also protecting the confidentiality of the accesses at the same time?
I haven't looked at both of it, so that's a collaboration.
Just to know.
Yeah?
Okay.
So I have, I think, less than 2 minutes left. This more or less tries to summarize what I tried to show you. Depending on where you are, you have these three curves. One of them is actually a straight line. This is what more or less, for one particular example, gives you what it means perfect privacy. It's a straight line. The first solution is more or less giving you privacy using, and I'll come back to that, a measure that is well below perfect privacy, while the second solution with the pool and the history comes pretty close to almost maintain perfect privacy. So what is the measurement? I don't have to tell the expert. Everybody uses the entropy measure in one way or another. So we used it also to more or less put a measure on how good your privacy is. And I don't have to tell you, the maximum value of the entropy is reached when the probability of every record to be the resulting one is the same, meaning perfect privacy. And the lower the value, the more the probability values will vary. Okay, I don't have time, as I already thought, to go into this EU project. Here we were really trying to go more on the practical side. And what we really tried to do, and I'll give you this very quick problem, consider here this situation. This guy runs a light and later on is taken a picture from. You somehow record the observation that somebody runs at El Camino this light with a certain license plate, and later on taking the camera, you know that it is James Bond. So by some deduction, you can find out it was James Bond who ran the light. Okay? So the question is not how to do this deduction, but how to prevent this deduction. And so we are not looking at this problem per se, but we really are trying to look at the problem in a more setting where we assume that people start to have internet access in their cars. They can access certain services like making reservations on the fly, doing credit card payments on the fly. And our goal or our aim is to ask what kind of properties should a system have, like this one, in order to be what we call privacy aware. So we believe that we cannot have perfect privacy as in theory, but what are the means, what are the techniques to come close to that more from a practical point of view? What kind of processes you need, what kind of policies you need, what kind of guarantees do you need between different components when they have to work together? Can you make some deduction if you know that the privacy that component maintains is X and this is Y? What's the combined privacy, including the communication guarantee or privacy for the communication between these two components? So this is in this very simple setting of this project our goal. I will not go through this and I will stop here. Yes, thank you very much. Any more questions? The lively person was the first row here.
Okay, just a quick one on this location privacy. Do you have any examples of kind of real-world examples where there have been problems with privacy, you know, where data has been misused?
For example, in Germany, they have just started to build up this Maut system, collecting money for the trucks going through Europe. And they have the devices that can tell the truck was at location sensitivity. You know which truck was at which point in time, and so they can track the route and they say this truck went that many miles on the highway, and therefore you have to pay Y. So this ability starts to scare certain people, because why not only doing it with trucks? You can also do it with simple cars. And why only collecting toll? You can also collect other things, data, okay? And we're trying to make this problem visible by going through this very simple hotel reservation and credit card example to ask, is it really, everybody would say, in order to pay for the credit card, you don't need any location information. So what kind of ways, abilities do you have to minimize the amount of data that is needed by, to track what is needed by these different services? How can you prevent that services are able to combine data? There are no explicit, or not that easy to find examples for that, but I think there will be. Like anybody is worried about this k-anonymity example, and I think this will have many, many more examples in the future.
I'll give you, later I'll give you, there is an example in the US
so
that's
you know
relevant to this, and I was wondering if you had any new ones, but we'll discuss that later. It is a real problem.
Okay. So you only wanted to test me if I had
I wanted to find out.
example.
I wanted to find out if you knew more than, if you knew some things I didn't yet know about. I was hoping the answer was yes. And so.
Any other question? So if you go to my website, type in Johann-Christoph Freytag, Humboldt University, you will find some of the papers. Not everything is there, because I still hope that one of my students will finish up the third algorithm with some more rigorous proofs than I presented here. Thank you very much.